So basically you can import it as import AxiomX dot calculus as C. It's your choice. You can put C A C, or also I'll tell you another alternative. You can say it as from AxiomX dot calculus import star. That also works. From there you just enter the functions directly. Now we have four functions under the calculus module. The first one is summation. It returns a summation, like it returns a sum in total with the lower bound and an upper bound as well. I'll tell you how. So I have this summation 1 float inf. It technically means infinity. And then we enter our sum, like our function. You can also put your function by the normal function like the def method, and then you just put the name. Don't put the brackets. That also works. This summation like 1 by x square, it if you sum it from 1 to infinity, it returns pi square by 6. If you want, you can just check it out. It's a standard value. The next one is c dot integrate. Now I'll tell you this. You put the function here, lambda x to the power of 4 into 1 minus x to the power of 4 divided by 1 plus x square. Zero to 1. So this will return pi minus 22 by 7. I mean 22 by 7 minus pi. It is always positive. Now print c done. Now we have the third function, that is the converges function. It actually checks if a given sum converges or diverges. So just enter the function. Okay. So when you enter this function, it will return true if it converges and it returns false when diverges. And then we have the next and the last function, c dot lim. It checks limits. This is just a beta version. It is not like, it may not be accurate at times. X plus 3 1, it will return 4. Now let's just run this. Just wait for it. So the first one was a summation. So it returned pi square by 6. It is 1.644. And then this one, it is pi minus 20, I mean 22 by 7 minus pi. And the third one, if it converges, it doesn't converge, so it returns false because it's a harmonic series. And then the limit, it returns 4. So this is how you can use our AxiomX.calculus package. You have learned to handle the AxiomX.calculus module. So now, if you want to make things more interesting, we also have the AxiomX.constants module. It's the same way you import, just like how you imported AxiomX.calculus. So you can enter like port AxiomX.constants as k, your choice. Now k, now it has a variety of constants. Standard math libraries like the default math library in Python only include pi, e, and tau, but then we have a wide range. Yeah, pi, e, tau, then the Gauss constant, lemniscate constant, then we have square roots of 2, 3, and 5, and then also golden ratio and silver ratio. Everything is there. So this is k dot pi. Now we also have a function called metallic ratio. It returns the metallic ratio of the order n. Okay, it's given by the formula n plus root of n square plus 4 by 2. So if the metallic ratio of order 1 is the golden ratio. If it is of order 2, it's the silver ratio. I'll show you an example. For this value 4.8, it's a rational number 5. And then we also have wide variety. We can also add Euler Mascheroni. It is 0.577 to 1. We also have golden ratio. So now let's see the output. See, pi is 3.141592. This is Euler Mascheroni constant. This is the golden ratio. And this is the metallic ratio of order 4.8. You have learned to deal with our AxiomX.calculus module as well as our AxiomX.constants module. Now we are going to deal with the AxiomX.functions module, which contains all kinds of arithmetic functions. It ranges from simple to complicated. So basically you import it the same way. Import AxiomX.functions as f. Now we have all kinds of functions. Like the simplest one is f dot absolute. It returns the absolute value of any number. If it is minus 6, it returns 6. If it is 7, it returns 7 itself. Now next one is f dot gamma. It's a crucial function in maths and it helps in calculating factorial of decimal numbers. Here I'm going to give gamma of 0.5. It's equal to root of pi. Okay. Now next one is f dot factorial. The factorial is actually calculated by the gamma function if it is a decimal number. Otherwise, it is calculated by multiplying preceding natural numbers. Now gamma of factorial of 0.5. It returns root of pi by 2. Trust me, it works. The next one is f dot sqrt. It returns the square root of any number according to Halley's method. Now square root of 3 is equal to 1.732. Okay. Next one is f dot cbrt. It calculates the cube root according to Newton-Raphson method. Cube root of 2. It returns 1.25992 something, right? Okay. Now next one is f dot zeta, the Riemann zeta function. So zeta of 2 is a very famous value and it is pi square by 6. And next one is f dot beta. That is also, there's also a famous function, value beta 3, which is equal to pi cube by 32. So now let's save this and run. So we handle the absolute value of minus 6 is 6. It is, and then the root of pi, that's gamma 0.5. Factorial of 0.5, square root of 3, cube root of 2, zeta of 2, and beta of 3. So you got to know how to use our Axiom X dot functions module. Now we go on to another interesting module of AxiomX, the AxiomX.exp module. It contains all the exponential and logarithmic functions. So I'll tell you how you import it. The same way how you imported all the previous modules. It's like import AxiomX.exp as E. Okay, we have four functions in the exp module. We have the first one, we have five functions in total, not four. We have five. So the first function is e.exp, the exponential function. It returns the Euler's number e to the power of x. Example, if I put exp2, it returns e square. And next one is e dot ln. It calculates the natural logarithm of x. So natural logarithm means the base of the logarithm is e itself. So ln of any number, any rational number is always irrational. Ln of 2 is a standard value. It is 0.69314 something. Now next one is e dot log 10. It returns a common logarithm of a number. Log 2, it returns 0.3010. Next one is e dot log 2 2. It returns 1 as the answer. Next one is e dot log the argument, that's 67 and 2. This will return some irrational value. Okay, now we save this and run. This is e square. This is natural logarithm of 2, common logarithm of 2, binary logarithm, this to the base 2. The binary logarithm of 2, and then this is the binary logarithm of 67. That is the base is 2. So this is how we implement the AxiomX.exp module. Now we move on to one of the most essential parts of any math library, trigonometric functions. For that, we AxiomX have created a specialized module named AxiomX.trig. So basically you can import it like the same way you've imported the previous modules as well. Import AxiomX.trig as T. Now, next is the functions that we have. We have radian and degree conversions. That is t dot radians. You enter the degree value over here. If you enter 180, it returns pi. Okay. Now we have print t dot degrees. Just enter any value, it returns a degree value. Now I'm entering 3.141592653589793. Exact value of pi, the 15 digits. Next one we have all the trigonometric functions: sine, cos, tan, cot, sec, and cosec. I'm not going to show all. I'll show you sine because everything depends on sine. Okay. Sine, we enter the argument in radians. So we enter our value t dot radians 30. Now next, and then we also have all the inverse functions. Okay, That is arcsine, arccos, arctan, arccot, arcsec, arccosec. So I'm only going to show you arcsine only because everything depends on arcsine as well. Arcsine of 1. It will return pi by 2. That's 1.570. So these are all the main functions that we have. I'm not gonna explain all, but then only few I've added because it's a lot. Now I'm saving it and I'm running it. See, this is a conversion of 180 degrees to radians, and this is what pi radians to degrees, and then this is a sine. It's accurate. Okay, trust me, it's accurate. We have calculated this using Taylor's series up to 30 terms. So it has been made as accurate as possible. And then we also have one point, and then this is the arctan of, arc sine of 90. So, arc sine of 1. So this is all for this, for the explanation of trig module. And now let's go on to the next module, AxiomX, the hyperbolic. The hyperbolic module of the AxiomX library contains all sorts of hyperbolic functions, which include sin h, cos h, tan h, cot h, sec h, and cosec h, along with their inverses. So basically, you can import it as import AxiomX dot hyperbolic as h. Now I am only going to show you sin h and arc sin h because the remaining functions all depend on sin h and arc sin h. Now let's start typing. Now let's save this and run this. So this is the value of sin h of 1 and this is the arc sin h of 1. So this is how you can use our axiom mixer hyperbolic module. But now gear up as you are going to no, you are not going to. You will be in a shock after seeing this. Matrix submodule helps in developing all the kind of matrices, all the operations you need, etc. Now to import this, you are using a different syntax. Import, from AxiomX dot matrix import matrix. Now if you want to create a matrix, you can create like this: matrix dot from list. Just enter your list, uh, like the list form of the matrix. 1, 2, 3, 4. Now we can print a, can print a dot determinant. To find determinant, you can put a dot det. It finds determinant for any square matrix. And then a dot inverse. It calculates the inverse of a matrix. This is the first set of inputs. Okay. I mean, now output. Okay. Now you can also multiply with that scalar quantity like 2. Now next one is the second setup. Now you can introduce a second matrix B and write 5 6 7 8. Now it prints a plus b, can print a star b, a into b, and then yeah, so that's how you do it. And then the next is how you can add zero and inverse matrices. So if you want to insert a zero matrix, you have to just enter the order like this, two, that means 2 rows and 3 columns, and then just enter c dot 0, and then you can print c. It returns a zero matrix of the order 2 by 3. And then d, if you want to put a identity matrix 4 by 4, you just put c dot, I mean d dot identity. You can print d. Now I'll show you the output. The first set of output, the matrix, the determinant, its inverse, and then when you multiply with 2, what will happen? And then when you added the second matrix and multiply the second matrix. And then I told you about the zero matrix thing, and this is the identity matrix thing. Okay, I hope you were pleased by this explanation of 0.1.2. And if you have any improvements, or if you want have any suggestions, or something you can add new, you can just comment under the video, and it would be highly appreciated if you patronize our project, our open source project. Thank you all and have a nice day.